Why is there something instead of nothing? Where did the material that created the Big Bang come from? These are questions that have intrigued humanity for generations. They are questions that transcend time, cultures, and civilizations, touching the core of our curiosity about the universe. The quest for answers to these questions has led to the development of numerous theories and the advancement of our scientific understanding, but there is still much we do not know. From the earliest philosophers to modern scientists, the origin of the universe has been a central topic of debate and investigation. Advances in technology and science have allowed us to look deeper into the cosmos and further back in time, but each discovery seems to bring even more questions. After all, if the universe began with the Big Bang, what existed before it? How can something arise from absolute nothingness? These fundamental questions continue to challenge our best efforts to understand the nature of existence. While the Big Bang theory is widely accepted as the best explanation for the origin of the universe, it does not answer all questions. There are still many mysteries and phenomena that remain unexplained. Let us now explore how the exploration of the universe, with the help of powerful telescopes like the James Webb and Hubble, has expanded our knowledge and revealed new secrets of the cosmos. The exploration of the universe has advanced extraordinarily thanks to powerful telescopes like the James Webb and Hubble. These incredible instruments have allowed us to observe cosmic events in unprecedented detail, revealing the birth and death of stars, cosmic collisions, and the presence of black holes. Each new discovery broadens our knowledge and helps us better understand the vast and complex universe we live in. The Hubble telescope, in operation since 1990, has been one of the main instruments in the exploration of the cosmos. It has provided us with stunning images of distant galaxies, nebulae, and other astronomical phenomena, allowing scientists to study the evolution of the universe over billions of years. Hubble also helped confirm the existence of dark energy, a mysterious force that appears to be accelerating the expansion of the universe. More recently, the James Webb Telescope, launched in 2021, promises to take this exploration to a new level. With its ability to observe the universe in infrared wavelengths, James Webb can penetrate through cosmic dust and observe the first galaxies that formed after the Big Bang. It will also enable detailed studies of exoplanets, looking for signs of atmospheres and possibly life. These technological advances are crucial for deepening our understanding of the universe and testing new theories about its origin and evolution. These observations and discoveries continue to challenge our existing theories, including the Big Bang theory. The Big Bang theory is widely accepted as the most plausible explanation for the origin of the universe. According to this theory, the universe began about 13.8 billion years ago from an extremely hot and dense state, rapidly expanding and creating the fundamental particles and forces we know today. However, there are various variations and complements to this theory that try to explain the mysteries and questions it leaves open. One of these variations suggests that the Big Bang may have originated from a state of cold, dark void. Before the Great Explosion, the universe would have been in an almost stationary state, without particles or radiation. Then, a quantum fluctuation caused a rapid expansion, leading to the birth of the universe. This idea helps explain the uniformity of the cosmic background radiation and the homogeneous distribution of matter in the cosmos. Another fascinating theory proposes that the universe is eternal, going through infinite cycles of expansion and contraction, a concept known as the cyclical model or oscillating universe. According to this idea, the Big Bang was not the absolute beginning, but merely the latest in an infinite series of Big Bangs, followed by Big Crunches. This theory challenges the notion of a linear timeline and suggests that the concept of before and after loses meaning in a perpetual cosmos. Additionally, there is the multiverse theory, which proposes the existence of multiple universes, each with its own physical laws. According to this theory, our universe may be just one bubble in an infinite sea of universes, each born from its own Big Bang. These alternative theories challenge the traditional view and open up new possibilities for understanding the true nature of the cosmos. The idea that the universe is eternal deeply challenges the notion of a linear timeline with a definite beginning and end. This cyclical model suggests that after each Big Bang, the universe eventually contracts into a Big Crunch, followed by another Big Bang, continuing indefinitely. This theory challenges the traditional view of a linear universe and suggests that the concept of before and after loses meaning in a perpetual cosmos. Another variation of this theory is the idea that multiple universes exist, each with its own physical laws and initial conditions. This concept, known as the multiverse, proposes that our universe is just a bubble in an infinite sea of universes. Each of these universes may have been born from its own Big Bang and may operate in fundamentally different ways. This further expands our understanding of the cosmos, suggesting that what we observe is just a small part of a much larger and more complex reality. An even more radical and fascinating theory is the idea that the universe could be a sophisticated program created by an advanced civilization or higher intelligence. According to this theory, known as the simulation hypothesis, everything we know, from fundamental particles to consciousness, would be a virtual construction, similar to a giant and complex computer game. This theory suggests that a sufficiently advanced civilization could have the technological capability to simulate an entire universe, with its own physical laws and initial conditions. In a simulated universe, everything we perceive as reality would actually be a digital representation created by a higher intelligence. The implications of this idea are profound, as they call into question the nature of reality and our role in it. If we live in a simulation, are our actions programmed, or do we have some degree of free will? Some scientists and philosophers argue that, given the speed of technological advancement, it is plausible that future or even extraterrestrial civilizations have already reached a level of sophistication capable of creating such simulations. They also suggest that if a civilization could create such an advanced simulation, they would likely create many of them. Therefore, the probability of us living in one of these simulations would be greater than that of living in the original reality. This theory not only challenges our understanding of the universe but also raises ethical and philosophical questions about the nature of existence, reality, and purpose. While some dismiss this idea as science fiction, others see it as a serious possibility that deserves investigation. This leads us to explore two of the biggest unknowns in modern cosmology: dark matter and dark energy. Together, these mysterious substances make up about 95% of the universe, but their exact natures are still unknown. Dark matter is an invisible form of matter that does not emit, absorb, or reflect light, making it undetectable by traditional observation methods. However, we know it exists due to its gravitational effects on visible matter, such as galaxies and galaxy clusters. Dark energy, on the other hand, is an enigmatic force that appears to be accelerating the expansion of the universe. Observations of distant supernovae and cosmic background radiation show that the universe's expansion rate is increasing, rather than slowing down as previously thought. The nature of dark energy is even more mysterious than that of dark matter, and its discovery has challenged many established theories about the evolution and ultimate fate of the universe. These two fundamental components of the cosmos raise important questions about the Big Bang theory and the structure of the universe. If dark matter and dark energy play such significant roles, how do they fit into our understanding of the origin of the universe? And what do their existences imply about the future of the cosmos? As scientists continue to investigate and test theories, discoveries about dark matter and dark energy have the potential to revolutionize our understanding of the universe. Let us now return to the Big Bang theory, which suggests that the universe began from an extremely hot and dense state about 13.8 billion years ago, and explore its implications and the questions that remain unanswered. The Big Bang theory is widely accepted as the most plausible explanation for the origin of the universe. According to this theory, the universe began about 13.8 billion years ago from an extremely hot and dense state. This initial event triggered a rapid expansion that continues to this day, giving rise to the fundamental particles and forces that make up everything we know. The cosmic microwave background radiation is one of the main pieces of evidence supporting this theory, acting as an echo of the Big Bang moment. However, despite its widespread acceptance, the Big Bang theory does not answer all questions. For example, it does not explain what caused the Big Bang in the first place or what existed before it. Some scientists suggest that before the Big Bang, all the matter and energy in the universe were compressed into a point of infinite density, known as a singularity. But this raises more questions than answers, such as, where did this singularity come from and why did it explode? Furthermore, the Big Bang theory does not explain why the universe is so homogeneous and isotropic on a large scale. The uniformity observed in the cosmic microwave background radiation and the distribution of galaxies suggests that there must have been some mechanism that smoothed the universe in its early moments. The cosmic inflation theory was proposed to solve this problem, suggesting that an extremely rapid expansion occurred a fraction of a second after the Big Bang, expanding the universe from a small homogeneous region. One of the biggest questions that the Big Bang theory leaves open is, what happened before the Big Bang? The theory suggests that time and space began with the Big Bang, but this idea is difficult to reconcile with our intuition about causality and temporal sequence. If time began with the Big Bang, is it possible to talk about a before? Another intriguing question is how all the matter, energy, space, and time could have originated from a point of infinite density, known as a singularity. Modern physics, including Einstein's general relativity theory, fails to describe the extreme conditions present in the singularity. The singularity is a point where our physical laws break down, and we need a theory of quantum gravity to fully understand these events. This leaves us with a large gap in our understanding of the origin of the universe. Additionally, the Big Bang theory does not explain the uniformity observed in the cosmic microwave background radiation and the distribution of galaxies in the universe. The cosmic inflation theory was proposed to solve this problem, suggesting that an extremely rapid expansion occurred a fraction of a second after the Big Bang. However, this theory, although widely accepted, still needs more solid empirical confirmation and leaves many questions open about the mechanisms and conditions that led to inflation. These unresolved questions show that despite great advances in cosmology, we are still far from fully understanding the origin and evolution of the universe. In the initial stages of the Big Bang, the universe was a hot and dense soup of subatomic particles, where the formation of stable matter, such as atoms, was impossible due to the extreme energy and temperature. During the first minutes after the Big Bang, the universe was in a plasma state, primarily composed of quarks, gluons, and other fundamental particles. This period is known as the quark-gluon epoch, where particles interacted intensely under extreme conditions. As the universe expanded and cooled, conditions began to favor the formation of more stable particles. About 3 minutes after the Big Bang, the temperature dropped to a level that allowed the formation of the first hydrogen and helium nuclei in a process called primordial nucleosynthesis. These nuclei were the primary building blocks of the universe, but complete atoms could not yet form because the universe was too hot for electrons to bind to the nuclei. It was only about 380,000 years after the Big Bang, during the epoch known as recombination, that the universe cooled enough for electrons to bind to nuclei, forming the first hydrogen and helium atoms. This process allowed cosmic background radiation to decouple from matter, making the universe transparent to radiation. The cosmic microwave background radiation we observe today is a remnant of this period, providing a snapshot of the universe when it was just a few 100,000 years old. This initial formation of matter laid the groundwork for the creation of the first stars and galaxies, leading to the complex structure we see in the current universe. Quantum theory revolutionized our understanding of the universe by introducing the concept that even in the apparent vacuum, there are dynamic energy fluctuations that can give rise to particles. These quantum fluctuations occur constantly on subatomic scales, creating pairs of particles and antiparticles that appear and annihilate almost instantly. This phenomenon, known as vacuum fluctuations, is a fundamental feature of the quantum field. During the early stages of the Big Bang, quantum fluctuations played a crucial role in forming the structures we see in the universe today. As the universe expanded and cooled, the small density variations caused by these fluctuations were amplified by cosmic inflation, a period of extremely rapid expansion that occurred a fraction of a second after the Big Bang. These density variations became the seeds for the formation of galaxies, stars, and other cosmic structures. Experiments and observations, such as those conducted by the COBE satellite and more recently by the Planck satellite, have confirmed the presence of these fluctuations in the cosmic microwave background radiation. The small irregularities observed in the background radiation correspond to the density variations caused by quantum fluctuations in the early universe. These observations provide powerful evidence for the inflation theory and the role of quantum fluctuations in forming the cosmos. These fluctuations not only help us understand the structure of the universe but also raise fascinating questions about the nature of spacetime itself and quantum mechanics. Let us now explore the Planck epoch, a period so early in the universe that our best physical theories break down, and how a complete theory of quantum gravity is needed to fully understand this era. The Planck epoch refers to the extremely early period of the universe, occurring up to 10 to the power of -43 seconds after the Big Bang. During this time, conditions were so extreme that our current physical theories cannot adequately describe them. The density and temperature were unimaginably high, and the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were likely unified into a single force. In this incredibly short timescale, known as Planck time, the quantum fluctuations of spacetime itself were significant. This means that the concept of time and space as we understand them disintegrates, and the quantum effects of gravity become dominant. To fully understand the events of this epoch, we need a theory that combines Einstein's general relativity, which describes gravity, with quantum mechanics, which describes the behavior of subatomic particles. This theory, often referred to as quantum gravity, has not yet been successfully formulated. One of the leading candidates for this theory is string theory, which proposes that fundamental particles are not points but rather small vibrating strings. The different vibrations of these strings correspond to different particles. String theory also suggests the existence of additional dimensions beyond the four we experience, 3 spatial and 1 temporal. If correct, this theory could unify all the fundamental forces of nature and provide a complete description of the universe from the Planck epoch onwards. Understanding this era is crucial as it contains the keys to many unresolved questions about the universe's origin and evolution. But what about the idea of the universe being cyclical? This is a theory proposed by physicist Roger Penrose, which challenges the idea of a universe with an absolute beginning and end. According to this theory, the universe undergoes infinite cycles of big bangs and big crunches. Each cycle, or aeon, begins with a big bang, expands, and eventually collapses into a big crunch, only to start again with another big bang. Penrose proposes that the extreme states of the universe at the end of a cycle, when it is in a state of high entropy and maximum expansion, become mathematically identical to the state of low entropy and extreme density that characterizes the Big Bang of a new cycle. This implies that the universe constantly renews itself, with each cycle inheriting some properties from the previous one. This idea challenges the notion of a single linear beginning, suggesting that time could be infinite both into the past and into the future. Conformal cyclic cosmology offers a potential explanation for the uniformity observed in the cosmic microwave background radiation and the homogeneous distribution of matter in the universe. If the universe has undergone multiple cycles of expansion and contraction, these processes could help smooth out any irregularities, resulting in the homogeneous structure we observe today. Additionally, this theory could provide a solution to the singularity problem, avoiding the need for an absolute beginning with infinite density. Despite its theoretical appeal, conformal cyclic cosmology still faces significant challenges. The main difficulty is finding observational evidence that supports the idea of infinite cosmic cycles. However, Penrose and other scientists continue to explore this theory, looking for signs in the cosmic microwave background that could indicate traces of previous cycles. The universe presents an intriguing duality in its nature. It is both deterministic and probabilistic. At the macroscopic level, many events appear to follow deterministic behavior, where specific initial conditions lead to predictable outcomes. The laws of classical physics, such as Newton's equations of motion, exemplify this view, allowing scientists to make precise predictions about the movement of large objects. However, when we delve into the subatomic world, quantum mechanics reveals a different reality, where probability reigns. Instead of precisely determining particle behavior, quantum mechanics provides only the probabilities of where a particle might be or how it might behave. Heisenberg's uncertainty principle, for example, states that we cannot simultaneously know a particle's position and momentum with infinite precision. This introduces a fundamental uncertainty into our understanding of particle behavior. This coexistence of determinism and probability can be seen in the nature of radioactive decay, where we can predict the decay rate of a large number of atoms but cannot predict exactly when a specific atom will decay. Similarly, quantum interference, where particles like photons exhibit interference patterns when passing through two slits, suggests that particles exist in multiple possible states until observed, at which point their probabilities collapse into a single reality. The quest for a theory of everything aims to unite these two seemingly contradictory views of the universe, integrating Einstein's deterministic general relativity with probabilistic quantum mechanics. Such a theory would provide a more comprehensive and unified understanding of the fundamental nature of the cosmos, addressing both predictable large-scale events and uncertain small-scale phenomena. And so we arrive at the theory of cosmic inflation, one of the most revolutionary ideas in modern cosmology. Initially proposed by Alan Guth in the 1980s, this theory suggests that the universe underwent an extremely rapid and exponential expansion a fraction of a second after the Big Bang. This period of cosmic inflation helped resolve several important problems in cosmology, such as the uniformity of the cosmic microwave background radiation and the flatness of the universe. Before inflation, the universe was a hot, dense soup of subatomic particles. During inflation, this soup expanded at an incredible speed, much faster than the speed of light. This rapid expansion stretched out any initial irregularities, making the universe incredibly homogeneous and isotropic. Inflation also explains why the universe is so flat. The rapid expansion smoothed out any initial curvature, resulting in a universe that appears perfectly flat on a large scale. One of the most important predictions of the inflation theory is the existence of quantum fluctuations that were stretched to macroscopic scales during inflation. These fluctuations are responsible for the small density variations that eventually became the seeds for galaxy and large structure formation in the universe. Observations of the cosmic microwave background radiation, especially by the COBE, WMAP, and Planck satellites, have provided strong evidence for these fluctuations, supporting the inflation theory. Although the inflation theory solves many problems and is supported by observations, it also raises new questions. One is the origin of the inflaton field that drove inflation. Another is the possibility that inflation never completely ended, resulting in a multiverse where different regions of space may have different physical properties. These ideas continue to be explored and tested as we seek a deeper understanding of the universe. The distinction between the philosophical concept of nothing and the scientific view of nothing is crucial for understanding the universe's origin. Philosophically, nothing is the complete absence of anything, no matter, energy, space, or time. This absolute nothing is an intriguing and paradoxical concept that raises the question of how something could arise from it. However, this philosophical view of nothing is quite different from what scientists consider as nothing. In science, nothing often refers to a quantum vacuum, which is not truly empty. Instead, the quantum vacuum is a state with the lowest possible energy, where virtual particles continuously emerge and vanish due to quantum fluctuations. These fluctuations are inherent to the very nature of spacetime and are predicted by quantum mechanics. Even in what appears to be a complete vacuum, quantum energy is still present, and this energy can give rise to particles and radiation. These quantum fluctuations form the basis for various theories about the universe's origin. Some physicists propose that the Big Bang could have been the result of a quantum fluctuation in a pre-existing vacuum. According to this view, the universe may have emerged from nothing, but this nothing is the quantum vacuum full of potentiality. This concept is supported by experiments demonstrating that particles can indeed spontaneously arise in a quantum vacuum. This scientific view of nothing challenges and complements traditional philosophical notions, offering a richer and more complex perspective on the universe's origin. It suggests that the universe may be a natural consequence of the laws of physics, where even the vacuum is not truly empty but a fertile field of quantum possibilities. Exploring the universe's origin leads us to question everything we thought we knew about cosmic creation. From traditional Big Bang theories to the latest discoveries and hypotheses, such as cosmic inflation, quantum fluctuations, and the idea of a multiverse, we realize that our understanding of the cosmos is constantly evolving. The notion that the universe may not have arisen from absolute nothingness but from a quantum vacuum full of potentiality opens new doors for scientific and philosophical investigation. These new pieces of evidence not only challenge the traditional view of the Big Bang but also invite us to reconsider the very nature of reality. We are only beginning to uncover the deep secrets of the cosmos, and each discovery brings us closer to understanding the true beginning of everything. As we continue this journey of exploration and discovery, one thing is certain: the universe is far vaster and more mysterious than we ever imagined. If you are as fascinated as we are by these new perspectives and want to continue exploring the mysteries of the cosmos, subscribe to the channel and turn on notifications. Don't miss the upcoming videos, where we will continue to uncover the secrets of the universe and explore the scientific discoveries that are transforming our understanding of reality. See you next time.